Hello, my name is Paul Hilling, and I am presenting the effects of lexicon size on solving bananagrams. This presentation is for the Internet Technology and Secure Transaction Conference in 2017. To give you a brief overview of my presentation, I will introduce bananagrams, review related work in Scrabble, pose the question I'm trying to answer, and share my methodology, preliminary results, and initial conclusions. Scrabble is a word game where players place lettered tiles on a board and compete for the high score. Scrabble is a game of incomplete information because players don't know what tiles other players have in their hands. There's also a lot of strategy in a game of Scrabble because there are various bonus squares on the board. This means that players have the option to play defensively and prevent their opponents from playing high-scoring words by taking advantages of these bonuses. Scrabble is a turn-based game. In tournament play, turns are limited to 25 minutes, so this is the time limit that Scrabble AIs, or artificial intelligences, have to beat. Scrabble also has 7 tile hands, which means that players can only hold 7 tiles at a time, which limits the kinds of words that players can play. Players draw from the pile to replenish their hand, and the game ends when players can't draw any more tiles and can't make any more words. On the other hand, Bananagrams is a word game where players compete to place all of their lettered tiles first. There's a caveat though. Even though players in 2 to 4 player games start with 21 tiles, players must draw a tile every time a player empties their hand. Bananagrams doesn't have a true board and can be played on any flat surface. Players each need their own space to play because Bananagrams players can only build off their own words. This limits player interaction. One of the interesting features of Bananagrams is that players can rearrange their letters as they see fit. This process is illustrated on the next slide. On the left, there is a snapshot from a game of Scrabble. You can observe the spatial constraints of playing on a conventional board. You can also observe the 7 tiles a player has in his hand in the upper left-hand corner, as well as the distribution of the various bonus squares which are red and blue throughout the board. On the right, there's a snapshot from a game of Bananagrams. In the first picture, the player drew the T tile. In order to play it, the player moved the D from food to tie to make tide, and then added the new T to foo to make foot. Because the player's hand is now empty, they would draw another tile to repeat the process. In order to understand how I might write a program to play Bananagrams, I needed to understand how other people used computers to play Scrabble. The DOG, or Directed Acyclic Word Graph, is the first fast word-finding algorithm and is the preferred data structure for storing word lists in contemporary Scrabble AIs. It is an improvement over the search tree because it collapses shared nodes together. This is shown by the image on the right. This image compares the tree and the dog for the words tap, taps, top, and tops. Because of the shared letters in these words, the dog can store the words in fewer nodes. Whereas both the tree and the dog can share prefixes, as shown by the T that roots each diagram, only the dog can share suffixes between the words, such as the S in taps and tops. As in a tree structure, the dog stores words as sequences of letters from start to finish. When applied to finding words in Scrabble, the dog only looks for words from left to right, or start to finish. This biases the words that AIs that use dogs can easily find. The GADAG is an improvement over the dog because it addresses the dog's directionality. GADAG is never defined in the paper, but I suspect it's a play on words because it's a directed graph that works both forwards and backwards. It is twice as fast as a dog, but 5 times as memory intensive, so it's only practical to use on modern machines. The GADAG stores a word as a series of each possible path, starting at any given letter. As you can imagine, this makes the GADAG a much larger data structure than a dog. For example, whereas a dog could store the word cat as C-A-T, the GADAG would store it as C-A-T, A-T-C, and T-A-C. The advantage to storing words this way is that it's easier to find words regardless of what letter you start from. Maven is the most well-known Scrabble AI. It uses simulated games to learn strategy and a dog to find moves. Some of the advantages to using a dog include its relative simplicity to implement and a reduced size compared to a GADAG, which is an important consideration for games that can be downloaded as apps, such as Scrabble. Although a GADAG would be faster, the dog is still fast enough to enable Maven to play competitively in tournaments which have 25-minute turn limits. Maven is also a very effective AI. At a 2006 tournament in Toronto, Maven went 30-6 overall against expert Scrabble players. One of the advantages that Maven has is that it knows 9-letter words. Because Scrabble has the 7-tile limit, many players in Scrabble programs only know words that are 7 letters or less. However, if a player can take advantage of letters that are already on the board, they can make longer words. The author of the paper cites an anecdote where he witnessed an expert Scrabble player play methadone, a 9-letter word. This inspired him to add longer words to Maven's dictionary. There is only a brief history of solving bananagrams. There are no scholarly articles on solving bananagrams. Google Scholar turned up a computer vision article that was supposed to take a picture of a bananagrams board and help the player play a word, but word suggestion is handled by sending data to an undisclosed anagram solving website. That's not to say there hasn't been any progress in the field. A Stanford University instructor published code written in a C language for a Bananagrams AI on their course website. It uses queuing to check all possible letter combinations and then plays the best word as determined by heuristics. Instead of playing through the whole game, it only solves for the first 21 tiles. It also uses an undisclosed word list. By now, I've shown that Bananagrams and Scrabble share some superficial similarities because they are both letter-tile-based word games. Because of these similarities, it might be possible to apply Scrabble research to Bananagrams. However, there are also some fundamental differences. Bananagrams is first and foremost a game of speed, where the player who can play all the tiles the fastest wins. There's a potential trade-off when it comes to lexicon size. On the one hand, it takes longer to check more words. On the other hand, there might be time savings if the player doesn't have to rearrange the board as often if they can find a word that fits. This leads to my research question. Which can play Bananagrams faster? A program with a small or a large dictionary? Even though there is a Bananagrams AI, I ended up writing my own. The Stanford University Bananagrams AI did not run on my machine. Because I am more proficient in Python than C++, it made sense for me to use a language I was more familiar with, so I can modify and troubleshoot the program more effectively. Writing it myself also allowed me to better document how my method works, so I could see more clearly where improvements could be made. My solver works in cycles, where the goal of each cycle is to place a word on the board or playing area. After playing the first word, the solver looks at a tile on the board and makes a list of all the words that can be played with this letter tile and the tiles in the hand. This is because Bananagrams players can only place words on the board if they play off words that are already there. Then, the possible words are sorted from best to worst. As I was developing this program, I tested several different ways of evaluating word quality. Playing the longest word allowed the program to experiment and search all the possible words, but less frequent letters like Q ended up never being played. Evaluating words based on their estimated difficulty, which I calculated as the sum of the frequencies of each letter, seemed like it would reward both long words and words with rare letters, but words ended up being so finely separated that playing the best word every time resulted in the same few final states, and these typically didn't use all the tiles in a hand. I found the Goldilocks quality by using a Scrabble score, or the score that a word would have in Scrabble based on its points value. This balanced both long words and words with rare letters, yet still provided the program with enough words to choose from. After this step, the program checks if the word fits by making sure it doesn't take up any spaces that are already occupied and that any other connections it might make with other words on the board are themselves still real words. If the word does fit, the next cycle can start. If no words fit after checking all the tiles on the board, then the program takes all the tiles off the board and starts over. In order to test my program and determine whether or not shorter or longer word lists were faster, I needed some freely available word lists. I found two. The first was the online Plain Text English Dictionary, or OPTED, which had about 105,000 words after filtering and processing. I had to download it as separate files for each letter, so these needed to be concatenated. The OPTED also had many words that wouldn't ordinarily be playable in a game of English words, like the word am, spelled AAM, which is a Dutch unit of measure not found in most English dictionaries. The OPTED also has dictionary entries for each letter in the alphabet, which isn't applicable to a game where one-letter words can't really be played. The second word list I found was Jeff Bolter's Scrabble Dictionary, which had about 178,000 words. This list was one file and appeared to only have unique entries, so I did not process it in any way. After running my test with these two word lists, I decided to try it on an even longer word list, the set of all unique words, or the union of the OPTED and Bolter's word list. This list had about 223,000 words. I was surprised by how long that list was because it indicated that many words weren't shared between the OPTED and Bolter's list. I tested these word lists on 100 randomly generated hands. The program generated the hands by randomly drawing 21 tiles at the start of each game, so the different word lists weren't tested on the same hands. This table shows the three conditions that I tested and the different variables that were measured. Leftovers is the average number of tiles left when the hand wins or times out. If the hand wins, then leftovers is 0. Time is the average time it took for the program to win or time out. Wins is the number of times out of 100 that the program successfully played all 21 tiles, and time to win is the average time it took a winning hand to be played. According to the data, the shortest word list, the OPTED, was faster than the longer word lists, both overall and for winning hands. Longer word lists were more likely to be able to solve a hand than shorter word lists. This supports the idea of a trade-off. There are several problems with my program. First, it is hard to tell if all 21 tiles can be played. As I was developing my program with different test hands, I noticed that some couldn't be solved. I didn't find any papers that might shed light on the matter. For now, I'm assuming that if the program can't solve a hand in 500 cycles, then the hand is impossible to solve, but there's probably a faster way to do this. Looking at the sample hand on screen, a random hand that I studied during development, I suspect that it is actually impossible to solve because the program can't make any keywords at the beginning using the OPTED. And the words made at the beginning should be a list of all the possible words that can be made with a given hand. Therefore, If there is a letter in the hand that can't be played in any words, then the hand cannot be solved. However, I suspect that there are less extreme cases than this that also can't be solved, but I don't know how to prove or disprove this. Another weakness of the program is that it starts over when it's stuck. In real life, Bananagrams players merely shuffle tiles around, such as at the beginning of the presentation when we saw food swapped for foot. However, it was hard to identify letters that were only part of one word and then decide which words and letters to pick, so I was unable to implement this feature during the time in which I was developing my program. Because I didn't implement either the dog or the gadag, checking words is potentially slow. I know from observing the outputs that finding words is the slowest step in the process. Storing the lexicon as a list in Python was faster than storing it as a dictionary, but there's still room for improvement. Also, my program searches the possible word arrangements by picking the best word it can find in any given cycle. But the local maximum in the board space isn't always a solution. There are a number of steps I could take with the program for improvements or future research. First, I could implement a dog or a gadag and observe how much faster the program runs. I could also find a way to quit seeming impossible hands faster, given that it takes about 50 minutes to quit, give or take a couple minutes depending on the word list. A time limit might be a better guideline than a turn limit. Or I could try having the program remember each final state it reaches, and then have it quit if a final state is observed too many times. A better word rearrangement method would also generate significant savings. I think that finding a word on the board and picking up the unshared letters is a good starting point. But I'm not sure how I would pick which words or letters to pick from. Another improvement could be picking words more effectively. Right now, the program picks the first best word it finds that fits on the board, but maybe picking the best word overall for each cycle could be better. The risk with doing that would be having the program pick the same word every time and always result in the same final state, even if it's not a solution. After the program runs faster, it would make sense to have the program play through a whole game of Bananagrams instead of just the first 21 tiles. In conclusion, I determined that it is faster to check a shorter word list than a longer one. I also determined that longer word lists are more likely to solve a set of 21 tiles than shorter ones.